Hello, calculus students. It's Mr. Hein again. Um, so today, this one is on evaluating limits, which we've done in chapter 1, and you did pretty well on that. But this will be a nice refresher of it. Maybe there's something you'll learn here about it, or just strengthen your already knowledge of it. So in general, when evaluating limits, is you plug in that limit. So whatever limit you want to approach, you more or less just plug that in. Now, if you plug in, infinity, plus or minus infinity, that's when we talk about end behavior, though. And those are the scenarios. So we're talking when the limit as x approaches either positive or negative infinity, we get into the scenarios of if it's small over big, that will approach 0. If it's big over small, and we're talking the highest power because that has precedence when we talk about things at the very large positive numbers and very small negative numbers. But if it's big over small, that will approach in positive or negative infinity. And if it's the same power over the same power, typically that approaches some horizontal asymptote. Okay. Now, the 0 is straightforward. That's the function y equals 0. Big over small, same over same. For these, the best way to check your answer is to use polynomial division. It is possible that you might be able to get the answer of the same over same without this, but it's good to just check to make sure you're on the right track. This one, the big over small, you should always use polynomial division, as that'll tell you how it's approaching infinity, because there are different ways to approach infinity. You can approach along 2x plus 5. You can approach plus negative 3x minus 1. There's different ways to approach positive and negative infinity. Right? So that's talking end behavior as x approaches infinity. But with limits, we're not always plugging in infinity. Sometimes we're plugging in values such as the limit as x approaches 2. So for those, we plug it in. But things to know when you plug it in is sometimes you won't be able to just plug it in because remember that you can't divide by 0. So there are situations when you can't divide by 0 where you might have to do some algebra first to simplify it. Simplify / rewrite. Things that might come in hand with algebra is factoring or multiplying by a conjugate. And a conjugate is it's the opposite. It's the pair of a square root, more or less. And we'll see that in an example down below. And sometimes maybe algebra doesn't even work, in which case, if algebra doesn't work, sometimes you just have to plug in numbers very close, as that will give you an approximation for, a pattern / approximation. So let's work through some examples so you can see this in action. You'll be doing it yourself because that's when the real learning happens. And let's see how we do. So example A, let's do the limit as x is approaching 2 of 2x squared minus 8 over x minus 2. Notice right away if I tried to plug in 2, I'd get 2 minus 2 on the bottom, which is 0, and you can't divide by 0. So here we have to do some algebra first. I'll be able to rewrite, keep putting holes in my paper because of the crack right there. I'll be able to rewrite this as 2 times x squared minus 4 over x minus 2, in which case the x squared minus 4 can become x plus 2, x minus 2 over x minus 2, in which these will cancel, which, yes, that means that there's a hole at x equals 2. That is what that means. But then, however, where we're at is now you're at the function 2 times x plus 2, in which now we can plug in 2 and get 2 plus 2 is 4 times 2, and we get 8. And there's our answer. Now, there is a hole at 2, but that's okay, because remember, limits can still approach each other. You can still, a limit can still exist even though the value isn't at that point, right? In which case it's not continuous, but the limit still exists. Part B. Example B. Let's do the limit as x approaches 0 of 3x to the third plus 5x squared plus 1 over 5x to the third plus 2x plus 5. So notice here, if I plug in 0, it's going to be nice, because if I plug in 0, those will go away, that'll go away, and you're just left with 1/5. So that one's a pretty quick one. Third example here, let's do the limit as x approaches infinity of 3x to the third minus 1 over 2x to the third plus 5x. So right off the bat, I see the same power, the highest power on top and bottom, and that's being the third power, in which I think, okay, that's going to take precedence, because the minusing 1 is not going to affect too much. Adding 5x is not going to affect too much, because this is going to grow so quick, the x to the third, these kind of get outmatched. They don't mean too much. In which these, then, infinity to the third would kind of go away, and we're thinking, at least I'm thinking, that it's going to approach 3/2. But this is what I mean. If you're not sure, check using polynomial division to rewrite this. So how many times does 2x to the third plus 5x go into 3x to the third minus 1? 2x to the third times what gives you 3x to the third? Well, that's 3/2, in which you'll get 3x to the third plus 15x over 2. And then if you subtract those, that goes to 0. And you'll get this right here, in which this won't go into this anymore, so that's your remainder, right? So I'll just go put plus some, I don't want to be lazy, don't do plus some, plus negative 15x over 2 minus 1. I realize I looked at the screen and you can't read that, over 2x to the cubed plus 5x. I'll rewrite this right now so that's clear. So we now have the limit as x approaches infinity of 3 over 2 plus negative 15x over 2 minus 1 over 2x to the cube plus 5x. So rewrote the original problem. This is the same thing, just simplified in a, or I don't even know if you call it simplified, but written in a different way. Which, if we plug infinity now, well, now we have small over big, which will approach 0. And we're just left with 3/2, in which our guess was correct. So this will approach the horizontal asymptote y equals 3/2, and that's great. Okay. Let's look at a few more scenarios that you might get to. So let's do question D over here. It's getting a bit chaotic. I'm saving paper. The limit as x approaches 1 of the square root of x minus 1 over x minus 1. Can't plug in 1 because I'd actually get 0 over 0, and we call that indeterminate. But we won't get there yet. But for now, we can't divide by 0, so let's see. So this is where you multiply by the conjugate, which would be the square root of x plus 1. Multiply that by top and bottom so you don't change the problem. What this will become x minus 1 on top, because x, square root of x times square root of x is x. The positive square root of x that gets multiplied there will cancel out with the negative square root of x that gets multiplied there, and negative 1 times negative 1 times positive 1 is negative 1. And on bottom, we'll have x minus 1 times square root of x plus 1, in which we'll see that those cancel to 1, and we're actually just left with the limit as x approaches 1 of 1 over square root of x plus 1, in which now we can plug that in and get 1/2. All right. And now E and D, I'm going to squeeze it in. So E, let's do the limit as x approaches 2 from the right of 3 over x minus 2. So now in this problem, there's no algebra you can do because there's nothing you can simplify. And you can't plug in 2 because you can't divide by 0. So here, maybe we try plugging a number very close to 2. So let's do from the right side. So maybe we'll do 2.01 and see what's happening. You plug in 2.01, you'd be at 3 over 0.01, which is 1/100th. And that gives you 300. Okay. What if we get even closer? So if I plug in 2.001, well, that's going to give me 3 over 1 over 1,000, which is 3,000. And what I'm seeing is that these are getting larger. So my guess is that this one, the limit as x approaches 2 from the right of 3 over x minus 2, is going to approach infinity. In which sometimes the books will say that this does not exist because, remember, we're evaluating limits. And infinity isn't really a value at 2. So they could call it sometimes does not exist. There is no limit as we approach 2 to infinity, as it's more so approaching a concept. All right. Now let's get to the back here. I want to do 2 more with you because these are going to pop up and it might solve your question before you ask me. Oh my gosh, a lot of examples. All right, limit as x approaches positive infinity of 3 to the x over x to the 7th. Right? Now, powers are stronger than polynomials. So this is actually, because exponentials are stronger than polynomials. No matter what degree it is, exponentials will rise quicker because polynomials are technically patterns through addition. This is getting a little bit more into it. And exponentials are patterns through multiplication. And multiplication always speeds up quicker than addition. But that's something else that's not relevant to this class necessarily. So here, 3 to the x is going to blow up faster than x to the 7th. So this is going to approach infinity. And sometimes, I don't even know if we can, I don't think we can do polynomial division here. So x to the 7th times what gives you 3 to the x? That's a little bit more complicated than where we're at right now. So we'll all just accept it as infinity. And this probably won't be a question we'll ask you what the end bit of your function is, as this one gets a little bit trickier. But be very careful, because if I was to just go to negative infinity of this same thing, well, if you do 3 to a really small number, a negative number, 3 to negative 1,000, remember that's a negative exponent how many times you're dividing that number. So in fact, this right now, when you do 3 to the negative infinity, that's getting very close to 0. And on bottom here, negative infinity to the 7th, well, that's just approaching negative infinity. That's going to keep getting larger and larger. Power of 7 is going to keep it negative. So this, in fact, is small over big, meaning we'll be approaching 0. So just be careful on those. Hope that helps. If not, you can always come to office hours, reach out to me via email or message, and I can help you from there. All right. Bye-bye.